How you doing?
Hi, Professor Younger, how are you?
Not too bad.
I think some of the students that were in the lab today had a little bit of confusion on on the exams and the homeworks
Okay,
in terms of the time and dates.
gotcha.
Um, I guess because there was like a discrepancy between so one of the syllabus,
Hmm.
and what's what was dated on Pearson,
Gotcha.
as well as I guess the test. I wasn't here last week. I don't know if you saw the email. I had to leave for a work trip all of a sudden, and I wasn't able to attend the online lecture due to because I was working. Um, but the test that's been posted for online, it's due by the 25th, correct?
Actually, I'm just looking at that now. Yeah, that was test two, which is 17, 18, 19, and 20. That was supposed to be the 25th. Yes.
Okay. Is it due by the 25th or is it a proctored Loctus
No, it's
browser?
online. So it's one of those ones where you're allowed to use your notebook, open notes, open
Okay.
book, but you
Oh,
have
got it,
a
got it.
amount of time.
Okay. Yeah, I know you didn't have a lecture on Wednesday last week. So you told us to watch the video.
Mhm.
And then I wasn't here Monday, so that's really the only class that I wasn't
We were
present
off
in.
Monday anyway, so you didn't miss
Oh,
anything.
you're right.
Yeah. So
You are right.
you're golden, man.
Um, so yeah. Okay, sounds good. I think that
Thank you.
clears it up, at least for me. So I appreciate it. Thank you.
No problem. Yeah, for those of you who had any questions, yes, test two, which is all my tests are comprehensive, so I could have just called this one test two on chapters 19 and 20, but I actually did a little bit more to make sure 17 and 18 were included in it. So I went ahead and left it as 17, 18, 19, and 20. Uh, that is due on the 25th. I noticed today that no one had taken it yet, and that was actually a good thing because it turned out one of the questions just stopped working, so I had to rebuild it today. I did rebuild it, and it's now the 25th. But I may be able, if someone needs a little bit more time, I might be able to give you a little bit of extension. But I think y'all have got more than enough time for that. And of course, the more we push that back, the closer adjacent tests will be, which I think the 28th of June, 27th or 28th of June, we're supposed to have a midterm that occurs in your lab. So that's a face-to-face midterm. And of course, we don't want too many on the same week that you're taking an in-class face-to-face midterm exam. So keep that in mind. I've got
So
a
are
little
we
bit of, go ahead, John.
Oh, sorry. So are we still anticipating the midterm to be on the 28th?
Yes, that those dates that
Okay.
we've got set for face-to-face meetings, they're sort of ingrained in the lab schedule. So they're definitely,
Okay.
we might change what chapters we cover, but we're definitely going to have tests on those days.
Okay. Sounds good. Thank you.
No problem. Anybody else have any questions? All right. So
Uh,
there's a little bit of a dilemma.
Professor,
Go ahead.
what's the chapter gonna be on the midterm more than likely?
Right now I'm looking at probably 17 through 22. I don't think I'll get to 23, but it might be 23 as well.
Okay, thank you.
Okay, no problem. So there's always a problem when you do something like I did, which was I basically give you a plethora of videos, way more than is normally covered in a class, of course. But I wanted you to have a lot of resources so you could jump right in chapter 21 and even chapter 22 and start working. But that was because I had to miss Wednesday. and I just wanted you to have plenty of stuff to rely on. But when you come back here, there's always a question, do I assume that they knew all that stuff or not? I'm gonna go on the assumption that that you are not in complete knowledge of chapter 21. Specifically, what I think is best about those videos and the actual demo videos that were made by MIT is that can cover that opening couple, maybe 10 pages or so of chapter 21, where they talk about charge, inductance, and charging by inductance and stuff like that. Those are very important considerations, and they're the big concepts here. By all means, look at any of my old videos where I describe that, and I even talk about those videos. Those are very helpful for you understanding how things happen. So I'm going to go with the assumption that you know that, because we've sort of been studying this kind of science since, fourth grade, fifth grade, something like that. But again, I know there's probably people that don't necessarily get it. So if you don't, let me know, and we can set up a private meeting, or I can, I'm actually leaning towards on Friday, maybe offering a 11 a.m. or possibly noon meeting. That's of course optional. And I also considered offering one at like 6 p.m. on Friday as well. That would be optional, but just another chance for y'all to ask me questions, and we could cover something like that. Or we could just, have a private Zoom meeting or office hour or something where I can discuss those things, because it's really important for you to understand what happens when you bring a very charged object near another object, especially if that object's a conductor. And then if that object's not a conductor, like for instance, you take a rubber balloon, you blow it up with air, and you tie a knot on the end, and then you rub it on, well, someone other than my head, because looking at this head right now, it appears to be no hair on there. But you rub it on your hair, and what happens is the rubber has a higher affinity for the electrons on the ball on the balloon than your head does. So the balloon steals electrons, and now the balloon is negatively charged. And if you're all knowing what I'm referring to, you can then take that balloon and walk up to a ceiling, which is made obviously of a non-conductor, drywall, plaster of Paris, that sort of stuff. Or you can put up against a wall, and it'll literally just stick to the wall. So all that stuff is concepts that you need to understand. So by all means, ask me about them if you have any problems, or set up a meeting with me or whatever. I'm going to jump in with Coulomb's law, and then Coulomb's law for electric fields. And then I'm going to start doing the brutal integration that's required in this chapter. And we'll continue throughout the next basically 9-10 chapters. We're going to have some pretty awesome mathematics that I love, and I hope you guys will appreciate it in some sense, and learn what to do with that. So does anybody have any questions before we get started? Right now I've got test 3 set tentatively to like the 27th. That's probably not going to be the due date, just because I've seen now that no one took the other one, and it's due on the 25th. So I might give a few more days, but to be honest with you, really should at least take a couple pokes at it, because that's supposed to be due the day of the final, or excuse me, of the midterm. So if you hadn't covered that test before you get to the midterm could be even worse. So definitely get started on trying to take that practice test for test 3, as well as making sure you finish by the 25th at 11:59 p.m. You finish test 2, which is an online test, which I've told you guys is open notes, open textbook. You're allowed to Google questions. The big thing is it's limited in time, and I really, if you're having to look up more than one every other practice test, you're probably not ready enough for this to have been a face-to-face test. And that's really the state we want you in when you're taking even an online test. I want you to have the comfort and the confidence of knowing that you can take this test and be able to look up stuff that you don't know, because inevitably there's going to be one question or two questions that have some key factor that you completely forgot or you never really understood. And I like you having that sense of confidence and stuff to be able to look it up. But I'm not trying to make you really good at looking up answers to questions really fast. That does you no good in engineering. That does you no good in physics. That does you no good in science in general. So I don't want you guys to become like some of the people I've known who did less than honest things to get through their undergraduate and graduate careers, only to find out once they got their job was immediately aware that they were not competent and were let go. And in a lot of cases, that was after they had bought very expensive homes, very expensive cars. They had let their spouse be a stay-at-home spouse with their child, and you know, that's a big life-changing deal if you find out all of a sudden, oh, I've got a degree in engineering, but I'm not knowledgeable about engineering at all, and I've been fired. So I'm just trying to help you guys prosper and profit from the things that I've seen and can tell you about. So any questions before I get started?
Yes, I just I wasn't here earlier. I had some question about this like all this homework like due days like just try to make sure that what is the chapter we need to finish for like before this weekend.
So let me I'm looking at my page right now, which is the Mastering Physics page. And I'm specifically looking up the assignments. And I think I moved another date back today for you guys, just for the record. As soon as this loads up, I'll tell you. So to date, we've only covered chapters 17 through maybe 21. I'm going to cover chapter 21 today, or at least the most difficult aspects of chapter 21 today.
Mhm.
And therefore, only those dates for chapters 17 through 21 are even remotely valid. The other ones, chapters 22 and beyond, are clearly not valid because we haven't covered them.
Okay, okay. Just want to
Does
make
that make
sure. So
sense?
pretty much everything to chapter 21.
Yes.
Okay.
Yeah.
My second question is there some kind of like practice test for the midterm that we can actually starting to try and this weekend because of
Yeah,
the midterm is
absolutely.
okay.
If you're taking the practice test for test 2,
Mhm.
that's preparing you for it. If you're taking any of the chapter tests for 17, 18, or excuse me, the chapter practice for chapter 17, 18, 19, 20, and 21 and 22, then those are helping you for it as well. And then test 3, the practice test is already up, so you can start taking that as well. And that's all but maybe one of the chapters might not be covered by that. I will put a separate practice final or practice midterm up. That'll probably be up today or tomorrow since it's about a week out. So you'll have
Okay.
that as well.
Yeah, I just want to make sure we get a practice midterm this weekend so we get time to practice.
Gotcha.
All right,
Yeah.
thank you.
I'm looking right now at the assignments they finally pulled up. Obviously, 17 through 20 are not really that relevant, but I'm seeing on here, for instance, chapter 23 was due on 6/18. Again, this is a matter of the way Mastering Physics just sort of
Mhm.
vomited my previous homework assignments in here. So really all you need to pay attention to is 17 through 21. I'm trying to even find chapter 21. There it is. Chapter 21, conceptual and homework are due on the 25th, which I think is this Sunday.
Yes.
That's probably fair, but I'll have a better feel for it. Matter of fact, let me go ahead and do this. I'm going to go ahead and change it to the 27th for those two, just because there's no telling what could happen here when I go to cover chapter 21. I might not get enough for me to feel comfortable with you guys. So I'm changing that to the 27th for chapter 21 conceptual and the 27th for chapter 21 homework. 22, I'm going to move back to the 27th conceptual, and 22, I'll move back to July 2nd for the 22 homework. That gives you more time. Actually, I really should stick that to the 27th, but that gives you more time than the test that will cover probably chapter 22. So be advised of that, but you can start it immediately. Okay.
Thank you, Professor.
No
Oh,
problem.
also, I saw we do have like 2 extra credits for homework.
Mhm.
Uh, is that due date same? Is the due date of this weekend? Or
I don't close it down. So the way I work with the extra credits is ideally you get it done by the due date, but if you don't, if you get it done before I grade it, then I give you full credit.
oh, great. Okay,
Okay, so you got plenty of time.
thank you. Just want to make sure so I don't have to worry about this weekend.
No problem. And I usually try to type in the explanation of what the extra credit is. If you ever get in there and I didn't put it in, you can contact me and I can pull up my notes for the day that I did it and see exactly what was covered. So I'll recall exactly what the extra credit is.
Thank you.
You're welcome, Gohan. Anybody else have any questions? All right. So what I'm going to start with is I am going to start with Coulomb's law. And Coulomb's law is a bit of a historically interesting thing, specifically because it's not really that clear. It's not really that clear exactly who, quote unquote, discovered Coulomb's law. So it turns out that Coulomb had done it. It also turns out that Ben Franklin here in America had done it. And it also turns out, if I remember correctly, I want to say Lord Cavendish had done it as well. That third one I might be misremembering, but the main thing is I wanted you to know that there were at least 3 people that all came up with this roughly the same time. We're certain, for instance, that Coulomb made it public first, so he's got the name for it, but it is kind of interesting that it didn't necessarily come out that way. And the experiment that you do to determine, for instance, the constant in it is completely a matter of doing an experiment just like the one we did for gravity. Specifically, you could take 2 masses. Oh, this is weird. You could take 2 masses and put them on the end of a very light rod, for instance, and fix them in space. And then you could take 2 other masses and put them on the ends of a light rod and hang them from a ribbon that's flat. And then that gravitational attraction between the 2 masses at one end and the other 2 masses at the other end will actually cause it to rotate. And that's a fairly straightforward engineering problem, is how much force does it take to cause a certain thing to twist. It's called torsion. And with that, you can actually determine the constant. So that's how you could do it. But in the end, what was discovered was that there's an electric force. We also call it the Coulomb force. And the electric force, unlike the gravitational force, can be both attractive or repulsive. Gravity, as far as we've been able to tell, is only an attractive force. But the electric force, or the Coulomb force, is attractive and repulsive. And what we know is that the force, Coulomb, is directly proportional to the product of the charges Q1 and Q2. So Q is the symbol we'll generally use for charge, but it's also inversely proportional to the square of the distance between them. In that sense, it's very much like gravity. And in fact, when you actually do the experiment, you can find that the Coulomb force is actually given by K, Q1, Q2 over R squared, and K is approximately equal to 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. But almost no one uses that K. Okay, we use it literally in like the first 3/4 of this chapter, and then we throw it out. A more common way of writing it is Q1, Q2 over, now here's the weird part, 4 pi epsilon naught times R squared. So that's the more typical way of writing it. And when we do that, we get epsilon 0 equals 8.85 times 10 to the negative 12th Coulomb squared per Newton meters squared. And hopefully you've already seen enough from your reading and from the videos to understand that the Coulomb is the unit of charge, and it's a ginormous unit. A whole Coulomb of charge is a lot of charge. Okay, just like a whole farad capacitor is a whole lot of capacitance. If you look at this K a little closer, you'll see that it's actually more like 8.99 times 10 to the 9th Newtons meters squared per Coulomb squared. But I gave you that figure of 9 for a very good reason. And the reason is that a lot of times I will choose numbers so that that number cancels out. And if you look at that number and think of it as 9, then you hopefully know that 1/9 is 0.111. So sometimes that just gives you a little advantage when you're doing calculations where you don't have to use a calculator. Now, for some perspective, what I will remind you is that the gravitational force is actually equal to G M1 M2 over R squared, where G is equal to is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So that's the gravitational constant. And in fact, it's quite instructive to calculate the basically the force to force ratio of the Coulomb force to the gravitational force for an actual physical object. And you'll from that see that there's really no reason to worry about gravity when you're doing electricity calculations. So let's look at that. Let's consider, for instance, a proton, which has a charge of E equals 1.602 times 10 to the negative 19th coulombs. And then orbiting about it, at least in the classical planetary model of the solar system, we have Q is equal to negative E, which equals negative 1.602 times 10 to the negative 19th coulombs. And we have the distance between them in the hydrogen atom, for instance, is something called the Bohr radius, which is 0.529 times 10 to the negative, I believe that's 10 to the negative 11th. Let me double check that real quick just to make sure before I write it down and commit to it. Bohr radius, Bohr radius. And there's actually a formula for it. So Bohr was actually able to work it out. It's 0.529 times 10, 292 actually. 292 times 10 to the negative. If I multiply that by, if I divide that by 10 and multiply that by 10, 10 to the negative 10th meters. Okay. So that's the actual distance. I actually wrote a subscript A on an A, which isn't right. I meant to write A sub 0 because it's the ground state. So that's what that is. Now, I'll also tell you that the same situation is going on with regards to gravity, but in the case of gravity, it's mass that matters, and the mass of the electron, M sub E, is equal to 9.109 times 10 to the negative 31st kilograms. And the mass of the proton, M sub P, is equal to 1.607 times 10 to the negative 27th kilograms. So hopefully that jogs a bell or jogs your memory so that you'll know what we're talking about here. I was just looking at some other conversion factors I found in here just to confirm everything I had was right. Yeah, that all looks good. 0.529 times 10 to the negative 10th meters. Yep. Okay. So let's go ahead and calculate what I was just referring to. So what I want to know is what is the ratio F Coulomb per F gravitational, or F Coulomb over F Newton, for the proton and electron in a hydrogen atom in the ground state. So the ground state is why I put that 0 on the A, because in fact, if you go to a higher end state, then the electron is actually a little bit further away for n equal 1, n equal 2, n equal 3. The higher n goes, the farther it is away. So hopefully that makes sense to you. So let's look at this. What I want to do, as I said, is calculate the ratio. And really, just remember, when I say calculate the ratio, what I'm really asking here is how much stronger is the Coulomb force than the gravitational force? Because if this number comes up to be 1 or bigger, then basically you have to multiply the gravitational force by a number that's bigger than 1 to get the Coulomb force. And in fact, if that number is really big, then you know the Coulomb force is much stronger. So the force of Coulomb divided by the force of gravity is equal to, I'll just use the K, Q1, Q2 over A0 squared divided by G, M1, M2 over A0 squared, because A is actually the distance between them. So that's pretty straightforward. That also allows us to realize that I didn't even need that number, because that's just going to cancel out. And in fact, what we're going to get is ignoring the signs, and that's an ongoing thing here, is we're always going to ignore the signs when we're doing computations with Gauss, with Coulomb's law. But I'm going to say K, and then in this case, since we're talking about electron and proton, they both have charges whose magnitude is E, right? The electron being negative E and the proton being positive E. And then that's going to be divided by the gravitational constant times the mass of the electron times the mass of the proton. So let me shut up my phone too. Okay. All right, I got that. So now I can go ahead and put this, and I'm going to say 8.99 times 10 to the 9th. Notice the whole thing would be newtons per newton. So ultimately the units are all going to work out. So I'm not even going to write the units this time. I'm going to write 1.602 times 10 to the negative 19. That's going to be squared. And then I'm going to divide it by 6.67 times 10 to the negative 11. Again, ignoring the units. And then 9.109 times 10 to the negative 31 times, again, this is in the bottom, so 1.607 times 10 to the negative 27th. Again, whoa. And that should give us our figure. So, of course, I don't even have my calculator. Maybe that's not good. Grab it real quick. My carpenter seems to have abandoned me, so I still haven't gotten my bookshelf made. I have a nice one right behind me now. So let's look at this. It's going to be 8.99 e to the 9th times 1.602 e to the negative 19th. I'm going to square that one. And then I'm going to say divided by parentheses 6.67 e to the negative 11 times 9.109 e to the negative 31 times 1.607 e to the negative 27. And it looks like I have 8.99 10 to the 9th, 1.602 10 to the negative 19th, squared 6.67 10 to the negative 11th in the bottom, 9.109 times 10 to the negative 31 in the bottom, and 1.607 times 10 to the negative 27th in the bottom, close parentheses. And this figure gives me, in fact, 2.36 times 10 to the 39th. So what that means is the electric force is on the order of 10 to the 39th times more powerful than the gravitational force. Okay. Let me pause for just a second. I have my daughter calling home. Hello. Yes, I am right now. Can I is everything okay? Yeah, you can come in. How you feeling? All right, love you. Bye-bye. Shawnee Sydney stopping by. All right, sorry everybody. I just wanted to my daughter had a root canal today, so I just want to make sure she was okay. She's been having some problems with her teeth. So sorry to interrupt my class like that. I wouldn't have answered it otherwise. So you can see the force of the electric force, the Coulomb force, is way, way stronger in this specific case than the gravitational force. And the only reason why we deal with gravity much more is that matter in general is not charged. It's much more normal to run into matter that's made up of atoms and molecules with the same number of electrons and protons in each atom or each molecule. Because of that, the net charge is zero, and because the net charge is zero, you have no attractive or repulsive electric force. So that being said, they have the same form, at least in terms of pre-relativity. Specifically, the force goes like 1 over r squared, which means there's literally no r that you can have such that the force is zero. Okay. You can get as close to zero as you want, but you're never going to get zero because there's no r value you can stick in there to make it zero. You literally have to take the limit as r approaches infinity. So in that sense, the gravitational force and the Coulomb force are in some sense universal forces, meaning they literally reach across the entire universe, provided the thing has a charge. Okay, any questions on that? All right. Now, the other part of Coulomb's law is also like the other part of Newton's law of gravity. Specifically, a sentence would have been made in the case of the Principia when they introduced gravity. A sentence was in there and it said that the force of attraction is proportional to the product of the masses and inversely proportional to the square of the distance between their centers of mass, and that the force of attraction would act along a line connecting the two center of masses of the particles. The same are of the masses. The same thing is true about the Coulomb force. Specifically, if you imagine a line going from the center of charge of one of the charges to through the center of charge of the other charge, then the force of attraction or repulsion will go along that line. In other words, will point along that line. And since we're dealing with vectors, they didn't have vectors back then, but since we're dealing with vectors, we now have to know the direction as well. So that's why we have to give that little description. So let's start by solving a somewhat simple problem. I'm starting with the harder problems like I always do in here because the easier examples I think are handled well by the book, whereas I could make slightly more difficult examples and you guys can get used to it that way. So let's imagine first off, I'm going to actually create a coordinate system so there'd be no ambiguity about where things are and what a particular angle of force means and stuff like that. So let's imagine for a second that this is the x-axis, this is the y-axis. Let's imagine that we have a charge in this case of negative 1.111 times 10 to the negative 10 coulombs, and that's going to be Q1. And then over here, some distance away, which I'm going to say is a distance of, let's say, is a distance of 4 meters. I'm going to have a charge Q2 equals 1.111 times 10 to the negative 10 coulombs. And if I go up here a distance of 3.00 meters, I'm going to have another charge up there, and this charge is going to be Q, and let's call this Q3. I'm going to say Q3 is in fact 25.0 times 10 to the negative 3 coulombs. What I would like to know is what is the net force on Q3 due to Q1 and Q2. Okay, so that's the question. All right, this will be excellent because it gives me an opportunity to show you not only how to calculate the Coulomb force, but also how to calculate the direction and all that good stuff. So for starters, I'm going to say my solution in blue goes like this. F3, which means the total force on object Q3, is equal to the force on object 3 due to object 1 plus the force on object 3 due to object 2. Okay, so that's the general rule. No matter any number of charges that you have, if you want to find the force on one of them, then you got to calculate the force of attraction or repulsion due to each of the other ones. Notice I'm saying each of the other ones, so you don't count a force of Q1 on itself or a force of Q3 on itself or anything like that. And you want to make sure you don't get into this common practice of using summations that would accidentally have you counting the same charge twice. So you want to keep track of that sort of stuff. So I like to write it out piecemeal like this, and then we're going to work it out. Now, the great thing about Coulomb's law is Coulomb's law gives us a very specific magnitude. It's K, Q1, Q2 over R squared. That's the magnitude. And by using the sentence part of it, it also gives us a direction. But we've got to decide what causes repulsion, what causes attraction, and then what does that mean in terms of the direction of the force. So we're always talking about, in this case, whatever the prefix is or whatever the subscript is that comes first, that's the one experiencing the force. Okay, and the other one's the one causing the force. So that's the way I use my subscripts, and most authors I've run into use it that way as well. I don't think I've ever seen one use it a different way. So just keep that in mind. So let's, for starters, the easiest case is to calculate F31. And notice I'm not putting a vector symbol on it. So I'm just going to say F31 is equal to 8.99 times 10 to the 9th newtons meter squared per Coulomb squared. Now I'm putting the units in so you can see once and for all how the units are working on this. Now the two charges are in fact Q3 is 25.0 times 10 to the negative 3 coulombs, which I could also write 25 microcoulombs. And then the Q1 is, notice it's negative, but notice I'm not going to write that negative. It's 1.111 times 10 to the negative 10 coulombs. And if you notice, that's the same thing as 0.1 times 10 to the negative. In other words, if I divided the 1.11 by 10, I'd get 0.1111. But if I divided it by 10, I have to multiply it by 10 as well. So that's the same thing as 0.1111 times 10 to the negative 9 coulombs. And this part right here, 0.1111, is the same thing essentially as 1 over 9. And this thing right here is essentially 9. That's the whole reason I did that. I'm just, trying to make the math as easy as possible. Now I've got to take this and divide it by the square of the distance between them. The square of the distance between them is the square of 3 meters. So I'm going to take this off and divide it by 3.00 meters squared. So when I multiply 0.99 or 0.1111 times 10 to the negative ninth times 9 times 10 to the ninth, that's all going to cancel out and just give me 1. So ultimately, I am left with 25.0 times 10 to the negative third. Notice how the units work out here. I've got meters squared is canceling out with these meters squared down here. I've got Coulomb squared is canceling out with these coulombs here. So I'm just left with newtons. So when I multiplied 9 times 10 to the ninth times 0.11 times 10 to the negative ninth, I got 1. That just left 25 times 10 to the negative third divided by 9. Because 3 squared is 9, and I shouldn't have put that in blue, in red. Now 9 only goes into 25 twice. That would be 18. So this, in fact, is 18.77. That's carrying 1 extra sig fig. 18.7. Actually, I should call it 7.8 since I'm rounding appropriately. So 18.78 newtons is the force on 3 as a result of 1. Now, hopefully you all know this from your reading and stuff, but like charges repel and unlike charges attract. These two charges, one was negative and the other one was positive. So they're unlike charges and therefore they attract. And what that means is the charge Q3 is being pulled towards the charge Q1. So I know that this force F31 points straight down this way. So I could, in fact, say that F31 as a vector is 18.78 newtons in the negative j hat direction. Okay. And the negative, of course, makes it point down. The j hat tells you it's pointing along the y-axis. And the negative with the j hat means it's pointing in the negative direction of the y-axis. Any questions on that? Okay. So you probably already noticed that I've got a 3, 4, 5 triangle. So clearly this distance from here to here is 5.00 meters. So I'm going to make use of that as well. So let me calculate F32. F32 is again 8.99 times 10 to the ninth. We've already seen how the units work out, so I'm going to ignore that part. And I'm going to say times F3, which is 25.0 times 10 to the negative 3. And then the other charge is 1.111 times 10 to the negative 10. And then all that's going to be divided by 25. And the reason why is 5 squared is 25. Okay. So in this case, the force F32 is going to be 8.99 times 10 to the ninth times 1/9 times 10 to the negative ninth. That's going to give you 1 again. And then the 25 divided by the 25 is going to give you 1. So this is in fact 1.00 times 10 to the negative 3 newtons. So that's the magnitude of that force is 10 to the negative 3 newtons. Ooh, and I left that off here. That's supposed to be times 10 to the negative 3. So make sure y'all correct that. Times 10 to the negative 3. And this one goes in here as well. Times 10 to the negative 3. Okay. So that's 18.78 times 10 to the negative 3 newtons in the negative j direction. And now I've got a magnitude of 1 times 10 to the negative 3 newtons. This one, on the other hand, is not along an axis. So it's a little more complicated. So let's look at this. First off, we're going to notice that both Q3 and Q2 are positive, so that means they're going to what? Repel or attract?
Repel.
Exactly. So both Q3 and Q2 are positive, and that implies they repel. And what that means is Q3 is trying to run away from Q2, and it's going to go in that line, in the direction of that line connecting them. So if I continue this line like this, I would see that this force is F32. Okay. So we've got to figure out what that is in terms of vectors. So there's a lot of neat ways you can do this. For instance, one thing you could do is you could actually make a vector that points from Q2 to Q3, and that could be done like this. So for instance, vector from, let's say, Q2 to Q3 is equal to, now here's the weird part. We're basically going to say, I'm going to make a vector. Remember, that's one of the ways we can write a vector is we can use a less than symbol and treat it like an ordered pair. But what I'm going to do is I'm going to take the X component of the position of the final one, which is 3. So I'm going to take 0 minus 4.00 meters. That's the X component of the vector. And then the Y component is what happens when you subtract the two Y components. So the Y component of vector 3 is 3 minus the Y component of the vector to Q2, which is 0. So you end up getting a vector of negative 4.00 meters, comma, 3.00 meters. That is a vector that points exactly the right way. I've even corrected it and make sure that it points up and to the left instead of down and to the right. Okay. Now that works. Now, if I took that force of 1 times 10 to the negative third newtons and multiplied it by that, I would be off by, anybody want to guess what factor I'd be off by? If I multiplied 1 times 10 to the negative third newtons times this vector, negative 4.3, how far would the magnitude be wrong by? What factor? Anyone? All right, well, here's the deal. Okay, so it turns out that whenever you multiply one vector by a scalar, the magnitude of the new vector is just the magnitude of the old vector times the scalar. Okay, so in this case, the vector that we just made, we know has a magnitude of 5 meters. So I'd end up having F32 if I just multiplied that 1 times 10 to the negative third newtons. If I just multiplied by that vector V, I would actually have a magnitude equal to 5 times 10 to the negative third Newton meters, which is not only wrong magnitude wise, but is even wrong unit wise. So it turns out if you have such a vector, you don't want to just blindly multiply it by the magnitude. But what you can do is you can make that vector into a unit vector whose magnitude is literally 1 unit, not 1 meter. And when you do that and multiply it by, it works. So now I can show you in the same, for instance, I can create the vector V hat Q2 to Q3. And the way I'm going to do that is I'm going to take the vector, which is negative 4.00 meters, comma, 3.00 meters. and I'm going to divide it by the magnitude. Now, that just means multiplying by the reciprocal of the magnitude. So don't get freaky thinking, oh, we're dividing in a vector and that doesn't make any sense. No, it just means multiply by the reciprocal. The magnitude of this vector is, in fact, 5.00 meters. So if you do that, now the vector will have a magnitude of negative 0.800. Notice the meter divided by the meter canceled out. And then the y component would be 0.600. Again, the unit canceled out. And you can even check the magnitude of that vector. If I take 0.8 and square it, and then I take 0.6 and square it, I add them together, I get 1. I take the square root of 1, I get 1. So I see that that magnitude does in fact suggest that it earned that little hat on it. Everybody see the little hat, the little up arrow head looking thing? That's the symbol we use to represent a unit vector. So I can, in principle, just multiply the magnitude times this unit vector, and that works. So again, with this for instance scenario, I can say that F3, 2 is equal to, since I was doing 1 times 10 to the negative third, this can be negative 0.800 times 10 to the negative third newtons in the I hat direction, plus 0.600 times 10 to the negative third newtons in the j hat direction. So that is the actual vector. Okay, so that's a nice, neat, concise way that you can always use. It's sort of overkill. You don't have to do that every time, and sometimes that might be more complicated than just working it out. The other thing we can do is we can realize, okay, wait a second, this angle right here is phi, which equals the tangent inverse of 3/4. And of course, the tangent inverse of 3 divided by 4 is equal to 36.87. So phi is equal to 36.87 degrees. And then that angle happens to be the same as this angle, phi. So I can say now that this is F3, 2 cosine phi, and this is F3, 2 sine of phi. So if I did that, then I'd say F3, 2 F3, 2 sub x would be 1.00 times 10 to the negative third newtons times, and notice I have to force the negative in there, so I'll put that negative sign right there. Okay, that's because it's pointing to the left. And then I'll take it times the cosine of 36.87 degrees. And I do cosine 36.87 times 1e to the negative 3 gives me negative, because the negative sign was already there, 0.800 times 10 to the negative 3 newtons. And similarly, F3, 2 sub y would be positive 1.00 10 to the negative third newtons times the sine. Whoa. Times the sine of 36.87 degrees. And that gives me positive 0.600 times 10 to the negative third newtons. Okay, so you see we got the same answer no matter which way we did. Does that make sense to everyone? Anybody have any questions on how we did that? So now that we have these two, we actually have them in a vector form that's quite nice. So I can just add the x components, which by the way, have an I hat next to it. And that looks a lot like, 2x. And the x component on the F32 looks a lot like, 4x. Whereas the y components look like, I don't know, 3y and 17y. You can't add unlike terms. Similarly, you can't add unlike terms in this scenario. So you can only add I components to I components. You can only add J components to J components. So I can say finally that F3, which is F3 1 plus F3 2 is equal to, quickly looking back, I see my F31 was negative 18.78 times 10 to the negative 3 newtons in the J hat direction, plus my F3 2 x component was 0.8 negative, so it'd be negative 0.800 times 10 to the negative 3 newtons I hat, plus positive 0.600 times 10 to the negative 3 newtons J hat. So I can only add like terms to like terms. So I'm doing negative 18.78 plus 0.6, both of them times 10 to the negative third. So I'm getting, in the case of the y or the x component, the I hat one, there is no other part. So that's just going to be negative 8.00 times 10 to the negative fourth newtons I hat, minus, in this case, it's going to be negative 18.78 plus 0.6. So that's going to be minus 18.18 times 10 to the negative 3 newtons in the J hat direction. That's the total force. Okay. And I might ask for it in IJK notation, in which case this would be exactly right. Okay. But you should also be able to write it back in magnitude and direction format. And if you'll notice here, when you looked at the original vector, I had a y component that could have possibly been positive, but there was a negative one that was being added to it. So it really depended on which one was bigger. Clearly the F31 was bigger. So that one made a negative X component, and a negative Y component. And the X component was in fact only one of them, and it was negative. So both of them should be in the negative direction. So that's consistent with what I got here. I'm going to draw my coordinate system again really quickly. This is my x-axis. This is my y-axis. And what I've discovered is that the x component is very, very small and points in the negative direction. In fact, it's so small, it's basically 0.8 times 10 to the negative third. So that's 0.000800 newtons that way. And then the y component is negative, but quite big. So I'm going to say the y component is like that. And even that's a gross under representation, but this is going to be negative 18. Well, actually, it's not, since it's times 10 to the negative 3, I could say negative 0.01818 newtons, like that. Okay. So that means the net vector F3 is this one. And I might want to consider what this angle right here is, and I'll call that theta. So I can already see that the magnitude of F3 is going to be the square root of 0.000800 newtons squared. It's actually negative, but you knew it was going to be squared, so I didn't have to do that. And the same thing with this one. This is 0.01818. Again, this is also a negative, but again, it's going to be squared, so it doesn't matter. I think you can tell that 0.0008 is going to be really, really small compared to 0.01818, and it might not even show up. So I'm going to say 0.0008 squared, and that gives me basically a decimal point followed by 6 zeros and a 6-4. So this is equal to the square root 0.123456664 Newton squared plus 0.01818 squared, and this gives me 0. And I'm writing all this out so we can see where the sig figs go. This would be 0.0003305 Newton squared. Now, this guy only had 3 sig figs, so that one right there, the 5 is not a sig fig. This one only had 3 sig figs, so technically I can carry an extra 0 there. So you can see the 3 and the 0 and the 5 ends up here. But that 5 is actually not even a sig fig, so it really doesn't register whatsoever. So we're really going to say the magnitude of this is essentially 0.0182 newtons. That's to the proper number of sig figs. Does that make sense to everyone? Okay, now I'm going to take the angle, and the angle should be equal to the inverse tangent of the opposite, which is 0.01818 divided by 0.000800. Now you can see that that's really going to be a very large angle, way bigger than 45 degrees. If the two were equal, it'd be 45 degrees. So we think this angle is going to be huge, even though it's sort of, it's definitely in the positive direction since we're going counterclockwise. But the main thing is I'm going to take the tangent inverse of 0.01818 divided by 0.0008. And that gives me 87.48 degrees. So yeah, that is a pretty big angle. What that means is now we can also say that F3 is equal to 0.0182 newtons at, now to get to the negative x-axis, we'd have to go 180 degrees. So I'm going to say 267.5 degrees. And that is, in fact, yet another way of expressing that answer. Does anybody have any questions there? Looks like you do not. So that's a good thing. I hope that means that you guys are getting it. The one thing I want to tell you is it's not doing that subtraction of points, which is what I did down there where I said, for instance, V from Q2 to Q3. That way always works, and it always gets you a vector, but it's always going to get you a vector that is, well, I should say, it's going to get you a vector that is not necessarily going to have a magnitude of 1. And even if it did have a magnitude of 1, it's certainly not going to have a magnitude of 1 unit. It's going to have a magnitude of 1 meter or something like that. So there's a danger in doing that if you're reckless and don't pay attention to all the details. But it is a brute force way that you can always calculate a vector is you take the final point minus the initial point and you change the ordinate and the abscissa. That's what the numbers are called inside of an ordered pair, is the ordinate and the abscissa. The abscissa being the x part and the ordinate being the y part. When you do that and then convert those ordinate and abscissas to actual components of vectors, then you actually have a vector that points from the beginning of the vector to the end of the vector. And then it's just a matter, if you want to multiply that by some magnitude to make the right magnitude, then you first need to basically make the vector into a unit vector. And you always can make a unit vector out of a vector by dividing the vector by its magnitude. This one, I chose a really nice triangle, a 3, 4, 5 triangle, so that I knew automatically that the vector -4, 3 had a magnitude of 5. And it was actually a magnitude of 5 meters, so that made it even better, because all I had to do was divide by 5 meters. And in so doing, I was able to get a unitless quantity. I did notice right here that this didn't turn out so pretty, so I'm going to fix this real quick and make it better. So this is 3.00, just like this is 4.00. And this part turned out kind of ugly too, come think of it. Not happy with that at all. There you go. So any questions on that? I want you to keep that in mind, everybody. Whenever you just brute force need a vector, you can always subtract 1 point from another. Remember, it's always the final point minus the initial point. So for instance, if I wanted it to point from Q2 to Q3, I had to take the coordinate of Q3, which is in fact 0, 3, and subtract from that the coordinate of Q2, which is in fact 4, 0. So that's why I did it in the order that I did it. And I did get exactly the right answer, as you can see from the bottom here. But the main thing is that's just 2 different ways that you can do it. Does anybody have any questions on that? All right, now here's another big problem. I'm going to stop sharing just a second so you can get an idea for this. So that answer is nice. And it's not unlike, in other words, when I say that answer, I mean Coulomb's law is a nice answer, and it gives us very actionable results. It gives us equations that we can use, and we can still use for the vast majority of problems today. We have discovered in the intervening time that there is something called quantum electrodynamics, and that is really at the microscopic level exactly how electricity and magnetism behaves. So that this Coulomb's law isn't exactly correct, no more than this Newton's law of gravity is exactly correct. But in both cases, they're exactly correct to the sizes that we deal with in everyday life. So you don't even have to worry about quantum electrodynamics or general relativity when dealing with Coulomb forces and gravitational forces. But still, there's a little ickiness to it. Specifically, Newton saw that when he solved this problem for gravity, it was sort of a magical or mysterious force that could reach out across space. For instance, the Earth reaching out across space and pulling on the moon, applying a force to it so that the moon would constantly accelerate towards the center of the Earth and therefore stay in a circle. That's called action at a distance. And it did bother Newton, and he wrote about it. But the deal is, he knew there was a lot of problems he could solve with this Newton's law of gravity without understanding the true answer of how that could do it. So he just said, I'm not going to be able to figure that out, but I'm going to use what I have learned. And in fact, he could immediately use Newton's laws of motion and this law of gravity And from that, he was able to derive Kepler's first law of gravitational motion, or first law of planetary motion. He could derive Kepler's second law of planetary motion, and he could derive Kepler's third law of planetary motion. So immediately he had this wonderful result that was saying, hey, this is why Kepler said what he said, when Kepler had no idea why it was like that. Kepler just saw the data and said that was what it was. So that was a really good reason. Plus, let's not forget that Newton actually used the idea of the sun, or excuse me, of the moon accelerating towards the earth to come up with the idea of the gravitational force and how big it was. And from that, he was able to basically show the reason that the moon orbited the earth. So he already had that result, and now he had Kepler's three laws of planetary motion. So it was obvious that this law of gravity, no matter how it worked properly. So when they came up with Coulomb's law, the same thing was at play. You still had action at a distance. You had, for instance, a proton reaching across space in a hydrogen atom, pulling on an electron, keeping it in orbit. But in this case, what they found worked out pretty well. It stayed working out. I'm sorry, I keep yawning. But when they tried the same thing with gravity, it didn't quite work out as nicely, and it took literally an Albert Einstein to fix it. So what did they do? What they did was they imagined that one of the charges is like a source of an aura. You know, I'm talking aura like the pseudoscience thing that, you know, hovers around a person when they're getting ready to have a seizure or something like that. And I say pseudoscience because a lot of times when people talk about your aura, they're talking about pseudosciences. But I will admit that when a person is about to have a seizure, they do have a very distinct disposition that's quite different from other things. So in that sense, it's a real thing. So what they imagine is that if you have two charges, according to Coulomb's law of force, those two are either attractive or repulsive, depending on if they're like signs or they're unlike signs. Remember, like signs repel and unlike signs attract one another. But what they're going to say is, instead of thinking of it that way, think of one of the charges as if it causes some deformation of space around it. It changes the aura of the space around it. And then this other charge comes in, for instance, and when it comes in, it's feeling the aura of space that's been altered by the other one. And it is, in fact, that aura that causes it to move as if there's a force acting on it. What that was ultimately termed was that one of the charges created an electric field, and the other charge replied or responded to the electric field by acting as if there was a force acting on it. So that turned out to work really well. And other than taking into account quantum electrodynamics, it works out really well. So if you look, for instance, at the force of Coulomb, you'd say force is equal to Q1, Q2 over 4 pi epsilon naught r squared. Well, what you could do is say, okay, assume Q1 creates the field. And I'll say the electric field. Because you could, in fact, say that Q2 causes the, and I know you're not looking at this right now, I'm getting ready to give that to you. Because you could, in fact, assume that Q2 is causing the electric field and Q1 is the one experiencing it. But I'm saying for this particular argument, let's just assume the other is the case. So I'm writing down Kepler's law. Dang it, neither one of those. I'm writing down Coulomb's law for the force of attraction or repulsion between two particles. And I'm slowly waiting for this to come up. Okay, so you assume that Q1 creates the electric field and Q2 feels the resulting force. If that's the case, then the part of the force that Q1 does might be taken as Q1 causes E, which is Q1 over 4 pi epsilon naught R squared, where R is any distance you are away from Q1. Okay. Then Q2 just applies Q2 to make F. Okay. What do I mean by that? Well, we're going to define the electric field E as basically the force due to 1, so I'll leave a little space and put a 1, divided by the charge Q2. But that's not quite right. And the reason why it's not quite right is if you're going to say that a charge Q1 creates a field, then by necessity, a charge Q2 would also create a field. Therefore, when you get them both in there, they've got two different fields, and the first field created by Q1 is being affected by the second field by Q2. So you really need to fix that a little bit. So I'm going to say almost, and say that ultimately what it becomes is that E, the electric field, notice I'm adding a vector symbol, is going to be defined as the limit as Q2 approaches 0. In other words, we're trying to, we'll try it with a Q2 that's small, and we'll divide the force by the charge Q2 and get an answer. And then we'll try it with a slightly smaller Q2. And if we want, for instance, 3 decimal places, if we find the answers the same to within 3 decimal places, we're good enough. We can leave it there. But if we find that it differs in those first 3 decimal places, then we try a smaller Q2 and do it again. And a smaller Q2 and do it again. In that case, it becomes the limit as Q2 approaches 0 of F underscore 1 over Q2. Okay. Now, in practice, all that means is E is equal to F over Q, or E is equal to 1 over Q times F, or the simplest way you can say F, the force, which comes out in newtons, is equal to the charge times the electric field. So that then you can see the electric field has units of newtons per Coulomb, and the force has units of newtons. Okay. So this is technically the nice rigid definition of what the electric field is. But in practice, this is what you use. Okay, we'll find out there is a even better unit of the electric field that we'll ultimately use. I'll write it down here. It's actually turns out to be volts per meter, but we're not ready to cover volts yet. So I'll leave it as newtons per Coulomb right now. But I just want you to know that that ultimately is going to be what it is. Does anybody have any questions on that? All right, now would be a good time for us to go ahead and take a 10-minute break. So everybody go ahead and take a 10-minute break. Be back here at 6:56. Okay, I'm going to stay here in case anybody has any questions, and I'll leave this up. But go ahead and take your break and come back in 10 minutes, and I'll be sitting here waiting for you.
I have a quick question.
Mhm.
For the one of the extra credit assignments, the first question, like in the first part of the question, it says between the proton and the electron, and then in the second part, it says proton and neutron, but it says the same proton and neutron.
That seems like a typo. Is that in the mastering physics?
No, that's the extra credit that's in Canvas.
Okay, so that's something I wrote. Well, that's not funny anymore because clearly somebody made a mistake and it's not me. Let me check it real quick. Can you believe that Mr. Younger made a mistake? That can't be right. No, Mr. Younger makes a lot of mistakes. Is it the 6/13/23 one, or how far is too far?
The 613 one.
Okay, let me check this. Okay, you're asked to one, calculate the gravitational force of attraction between the proton, electron, and the hydrogen atom. Calculate the Coulomb force of attraction between the same proton and there you go. Thank you for catching that. That's nice. Now I can use it next year and next semester. And I'm just going to change that to electron. Appreciate that. Yeah, it's supposed to be electron. Then it says calculate the Coulomb force of attraction divided by the gravitational attraction. To this end, you should use at least 4 sig figs, and that will require you to look up the charge of an electron, the charge of a proton, and the Bohr radius for the n=1 hydrogen atom. And ideally, you can do part 3 symbolically and supply the numerical answer to 4 sig figs. Note, none of these calculations should provide a negative answer. So that's just me going on, like I was telling you earlier, is I never put the signs in for charges when I'm using Coulomb's law, but so I wouldn't bother doing that. Just use your understanding of physics to decide which direction the force will point and just multiply all positive numbers to get the magnitude. I did fix that. Thanks. Appreciate it, Drew.
I figured that's what it was. I was double checking though.
Yeah, that's crazy. I don't even know why the election came into my mind, but here it is.
No worries.
I liked it better when I thought Gene Coley made a mistake. All right, so I'm back on here. That's fixed. And by the way, I told Bohan this earlier in case anybody else didn't hear it. I put those extra credits up usually on the same day that I come up with them. And usually I make them due like a week later or 9 days later or something like that. But to be honest with you, if you get it posted before I grade it, I'm going to give you full credit whether it's late or not. And even then, if you make a small mistake, then I'll either go ahead and give you the full 100, or I will say, hey, you made this mistake, correct it, and then I'll give you the full 100. So keep that in mind. That's how we're going to do that. Anybody else have anything?
I had a question about, so you write all this stuff on these like scratch pads. Do you save these documents?
Right. Yes. They're in my Google Docs.
Is there any way that we have access to them already that I don't know about? Or would
Yeah.
it be
If
possible?
you go into the Canvas for my course, it says helpful documents and links. And if you scroll down to the very bottom of that module that says helpful documents and links, you'll see Mr. Younger's PHY 242 Google Drive. And if you click on that, that's where all those are, not only from this semester, but from every past semester. So when you look up on my YouTube channel, there will be a name associated with the video for that day. Like, for instance, today's name is PHY 242 N01C. I think y'all can tell where all that's coming from. PHY 242 N01C. And then I have an underscore 06212023. So you see that's today's date. So if you just do a Google search for 06212023, boom, you'll find it in my Google Docs. They're in PDF form. They're already there. And often I'll even carry on more stuff. Like after you guys leave, I might finish a problem, or I might answer a student's question and work that out. You'll see that at the end, that sort of stuff. But yeah, by all means, check them out. That's why I gave you access to them.
Perfect. Sorry, I missed the first day of class, so I think I probably missed that.
Yeah, that's okay. No problem. Even if you were here the first day, most people forget it anyway. So you're all good. Anyone else? Yes. Got about 5 more minutes. I'm going to check the interwebs and see what's happening in the world. Nothing exciting there. Well, that was depressing. Checked the news and found someone locally was arrested for murder. Someone was nice enough to give a person a home and person killed them. So that sucks. I'm not looking at news anymore. I'm gonna look at The Simpsons. Got about 2 more minutes, everybody. Got about 1 more minute. Okay. So I've got a few things I want to go ahead and cover. This is it's now been 10 minutes. So if you look now and realize that the Coulomb's law for force is Q1 Q2 over 4 pi epsilon naught r squared, you can sort of use this idea of what the electric field is. And when I say the word field, mathematically, what I mean is you're assigning to, in principle, it could literally be every point in the universe. So you imagine some coordinate system that you chose or that someone else chose, doesn't really matter. The main thing is someone's got to choose which direction is going to be the positive x direction, which direction 90 degrees from that's going to be the positive y direction, and which direction 90 degrees from both of those and right-handed is going to be the positive z direction, and where are those three axes going to coincide so that they make the origin. Once you have that, then you can have sort of a coordinate system that spans the entire universe. Okay. Now, if you take and assign to each point in the universe, which obviously there's literally an infinity of points, even between x equals 0 and x equals 1, with y equal 3 meters and z equal 3 meters, there's literally an infinity of points there alone. But still, you're going to assign to every point in the universe, or every point in some fraction of the space where you're defining this field, you're going to define a value. If that value is a scalar, then it's going to be a scalar field. For instance, you might plot every point in this room as by giving it a temperature that it actually has at that particular point. That would be a scalar field. It would be the temperature field. Or it could be a vector quantity, like the case of the electric force or the electric field, in which case it would be a vector quantity. So not only does it have a magnitude, it's got a direction associated with it, and that's being assigned to each point in space. Again, that can be some small fraction of the universe that you're deciding to define it on, or it can be the entire universe. The main thing is it doesn't matter. It's just going to be an assignment to every point in space, or to some set of points in space, an assignment of an x component, y component, z component. That could fit the bill for a vector. Or you could say the assignment of a magnitude and direction, that could fit the bill for a vector as well. So that's what I mean when I say something like a gravitational field or electric field or a scalar field. Now, in order for us to deal with that, we just needed to know roughly what a field was. But again, if you consider Newton's law of if you consider Coulomb's law of force, what you see is that the force law is equal to Q, and let's say Q big Q, over 4 pi epsilon naught r squared. So if you look at that with the idea of the electric field above, you can say, oh, well, the electric field caused by charge big Q is going to be Q over 4 pi epsilon naught r squared. And then the direction of the E field will be the direction that a positive charge would be compelled to move. So if you go some distance r away from big Q and you decide, here's a point, right? And you say, I want to know what the electric field is right here at this point. Well, you measure how far that point is away from the charge big Q. You take big Q, the actual magnitude of that charge, and you divide it by 4 times pi times epsilon naught times the square of the distance between that point and the Q, and that'll give you the magnitude. Now, if you imagine putting a positive charge there and say, which direction is that charge compelled to move, that will be how we define the direction of the electric field. Okay. And then, like I said, with the formulas above, if you wanted to know the force on a charged little q there, all you have to do is multiply E by little q, and that will give you the original formula we had. So we now have another formula for the electric field, at least in magnitude, and that includes a description of the actual direction. Okay. So that's how we actually compute what an electric field is. And in fact, the electric field doesn't have to be made up of individual point charges. It can have an electric field due to just one charge, big Q, but it can also have electric fields E. You can have an electric field E that's equal to Q1 over 4 pi epsilon naught. And then the distance would be between P and 1 squared plus, and I'm going to put a big vector symbol over it where we're making the understanding that clearly I'm going to have to work out the vectorness of it. Q2 over 4 pi epsilon naught R P2, again, where P is the point in question, plus dot, dot, dot. So if you have a bunch of charges, each one of those contributes a little electric field given by Q over 4 pi epsilon naught R squared, so on and so forth. Oh, I wrote a vector down there instead of an actual exponent. So that was helpful. Okay. Like that. And actually, I didn't really like how I did this one either. So let's blow that up too. Okay. So you could do that for any number of charges. And that's actually how you go about computing the electric field due to any number of charges. So that's another formula we could use. Your book has something equivalent to it as well. And again, I'm just putting that vector there because what's going to happen is you're going to have to draw a line connecting the point P to the charge Q1. And then depending on whether Q1's positive or negative, you'd have to decide where which direction a positive charge at P would have to move. And in fact, you might even want to subscript this P just to let everybody know that, hey, this is the electric field at P due to all those other charges at their various positions. Okay. Does that make sense? Anybody not understand that? It's a lot of words. So, don't feel bad if you don't understand it. The good news is you can always go back and listen to the recording again. So that's how that works. Now, that also means there's another way we could do it, and that is that the electric field, the differential electric field, if you will, I hate that. The electric field, at least a small electric field, DE, is equal to a small charge dq divided by 4 pi epsilon naught r squared with a vector symbol over it again, meaning I've got to work out the details. But that's an actual way to go about putting up a electric field due to a charge distribution that is, in fact, instead of being discrete, it's continuous, and they're infinitesimally small individual contributions. So if you think about that for a second, we can imagine, for instance, a XYZ coordinate system like this. This will be X, this will be Y, and this will be Z. Notice if I point my right hand, I point my index finger like I'm pointing at someone, put my middle finger perpendicular to that, and then my thumb is perpendicular to both of them. The index finger should point in the direction of the x-axis. Then you should move your hand so that the middle finger can point in the direction of the positive y-axis, and then your z-axis has to point in the direction of the thumb. The positive side does. If not, it's a left-handed coordinate system and all sorts of math goes crazy, so don't do that. Okay. So what I'm going to do is I'm going to imagine that there's a little chunk of charge out here, and that chunk of charge maybe is right here, and that's dq. I'm going to say that there is a vector r sub dq that points from the origin of my coordinate system to the actual location of that differential charge element dq. I'm also going to say that there is a point in space right here called P, and that point P is where we wish to know the electric field. So there's going to be a vector that points from the origin to it as well. And that point, that vector is going to be called RP. Now, if this charge dq is positive, which we're going to go on the assumption that it is, and then if it turns out to be negative, you'll slip a negative number in there, and the result will turn the vector that we get around backwards, which is exactly what you want it to do. So we've lost no generality by doing it this way. But what we know is if that is the little differential charge element Q or dq, and P is the location, according to our original law of Coulomb, the force of attraction or repulsion should be along the line connecting those 2 points. So imagine a line connecting Q and P. Now, well, I should say DQ and P. So imagine the line connecting DQ and P. That line looks something like this. Now, that's a line in 3-dimensional space. And in fact, if the charge dq is positive, then that would mean that the electric field should point from the dq towards the P. Does everybody understand why that's the case? The electric field should point from the dq towards the P. Anybody need some explanation of that? All right, so I'll give a quick little description either way since no one asked, but the electric field is defined to point in the direction that a positive charge would be compelled to move if it was in the electric field. According to Coulomb's law, if you have a charge dq at one location and another charge at P, okay, if you assume P is positive, then P is going to have a force on it that points in the same direction as the electric field. So if you imagine 2 positive charges, one at dq and one at P, then the one at P would definitely feel a force pointing along that black dotted line that I showed, but in the direction as if it left dq and headed towards P. So my question to you, and I rarely, if ever, get a student to get this right, but by all means, give me a try if you can. Can anybody tell me how I might use RP and RDQ to find a vector that points from DQ to P? So anyone? I've written it now in question form. It says, what vector, parentheses, in terms of RDQ and RP, points from DQ's position to P? Anybody know of a vector that we could say points from the end of RDQ to the end of RP? Anyone? Okay, I am going to call this vector. I'm going to call this vector RPDQ, which is in fact RP minus RDQ. So that's actually the vector. Notice if you actually computed that RP minus RDQ, you would take and flip the direction of RDQ, putting the head down at the origin and the tail up at DQ, and then you'd have 2 vectors that are head to tail, And clearly, if you ran from the tail of the first to the head of the last, you would get the vector right here. Which is RP dq, which is defined to be RP minus RdQ. Okay, so that's a really big thing. That's something that I can now use. And in order to use it, I need some extra stuff. Okay, this is sort of like when we were calculating centers of mass in the first 241 class. But basically, we have a charge density. Okay, I'm going to say charge densities. And one of them is lambda, and that's defined to be dq over dl. So that's like coulombs per meter. And it might be a constant, but it might also be a function of x, or a function of y, or a function of z, or a function of r, or a function of theta. There's also a sigma, which is defined to be dq over dA, where A is an area. So this is coulombs per square meter. And there's also a rho, which is defined to be dq over dV, where V is a volume. So this would be like coulombs per cubic meter. And again, each of these can be functions, or they can be constants, or whatever. If they're constants, that's called uniformly distributed. So I'm going to now say we have a Coulomb's law for the electric force. So here's the for the electric field, Coulomb's law for the electric field due to a continuous charge distribution. Okay, what it is dE, the electric field, due to a small section of charge dQ. And again, dQ can be lambda dL, it can be sigma dA, it can be rho dV. That's the key point. That's how I'm going to use those expressions across the top. I'm going to say dQ is either lambda times dL, or sigma times dA, or rho times dV. And I might even have a functional value of rho, sigma, or lambda. But all of this is going to be divided by 4 pi epsilon naught. Now I'm going to take the magnitude of that vector, RP minus RdQ, which we called RP dQ. I'm going to take the magnitude of that vector, and here's the weird part. I'm going to cube it. And the reason I'm going to cube it is because I need to multiply this electric field strength by the vector RP minus RdQ, which is RP dQ. But if I do that, the actual magnitude will go up by the magnitude of that vector. I don't want that. So I need to make it a unit vector. And if I make it a unit vector, that would be RP dQ divided by the magnitude of RP dQ. That's why I get a 3 down here instead of a 2. So I'm going to say times RP dQ. So that is actually the formula. This is one you will not see in your book, but you are allowed and should have it on your equation sheet when you take a midterm or test on chapter 21. Now, it looks a little confusing, and I'm going to show you with an example right now how to compute it. And what you need is dq, and you need RP, and you need RdQ. So RP minus RdQ is the definition of RP-dQ. So with that and this equation, you got everything you need. So what am I going to do? I'm going to take a coordinate system again, and I am going to draw it right here. And I'm going to draw the x-axis right here. Okay. I'm going to say that's my x, and this is my y. And now I'm going to imagine a bit of wire that's actually charged up. Okay. And in fact, this wire goes on to negative infinity down here and goes on to positive infinity up there. And if I cut off a single centimeter of it, and I measured how much charge in that single centimeter there was, and then I divided that charge by 1 centimeter, I would get a charge per unit length in coulombs per centimeter. If I then took any other 1 centimeter chunk, I would get exactly the same number. And that's a way of describing uniformly distributed charge. So a uniformly distributed charge lambda is on the wire, and we want to know the electric field I left off an L. So the electric field caused by the wire at x comma y equals, let's say, r comma 0. Okay. So this is how we're going to work this out. We're going to assume this thing goes on forever. First thing I'm going to do is identify my vectors. I need a vector that points to the point P. According to the problem, this is the point P. So according to the original drawing, the vector RP points from the origin to the point P. So that must be RP. And now, either on an axis connected to the first quadrant or any point on the first quadrant is where you should choose an arbitrary charge element. So what I'm going to do here is I'm going to say that right here is a differential charge element, dq, which is going to be equal to lambda times dy. Actually, let's undo all that, and I'll say it like this: dq equals lambda times dy. In other words, the height of that little blue chunk is dy. That means the bottom of it is a distance y from the origin, and then the top of it is a distance y plus dy from the origin. And that also tells us that the vector right here is r dq. Okay. Now, can anybody tell me what the components of r dq are? So what's the x component and what's the y component of r dq? I actually said everything, even though it's not actually drawn on here. Anybody want to give me the x component of r dq? Does anyone believe that the vector r dq has a non-zero x component? Yes, John. Yes, it doesn't have a non-zero x component. In fact, it's a vertical vector. It points from the origin along the y-axis, and it points in the positive y direction. Does anybody know how far or how long that vector RDQ is? I mentioned it a second ago with a very specific symbol. So how long is RDQ? Anyone?
Infinitely long?
What did you say that was? I'm sorry. Oh, I just found my chats were binging. You guys were probably answering all this time. I feel bad now. I'm sorry.
Is it infinitely long?
It will go to infinitely long, but right now it has a very specific distance up from the origin to the bottom of that little blue part. Do y'all remember what I said was that distance? I will draw it here now. It's along the y-axis, so you might suspect that this distance right here is just plain y. And then this distance is dy. So I'm going to go ahead and write this, and I suspect you're all going to kick yourself in the butt when you see it, but RDQ is in fact y times j hat. Now that we have that knowledge, is anybody willing to tell me what the y component of RP is? Very good, Helron. Yes, it has no y component because it's completely horizontal. It's along the x-axis. Can anybody tell me how long the vector r sub p is?
I'm assuming X and I have.
It is, yeah, you could do that, but I specifically gave it a value and drew it on there. But what you're saying is absolutely right. It's just you didn't notice that I actually gave a statement of how long that is. Do you see now on the diagram how long it is? You see the little red R that I drew?
It's that part, but yes, I see.
Yeah, that's why I wrote x comma y equals r comma 0. So that seems like a very specific point in space, but because this thing's infinitely long, that's a completely arbitrary point in space. What I'm saying is any point in space that has a perpendicular distance from the center of the wire of charge to it being r, that is the point that we're asking. So this actually answers an infinity of questions. It answers exactly how strong the electric field will be at any distance r away from the charged wire, assuming that you measure that distance perpendicular to the wire. All right. If you look at this, I guess you could probably immediately figure out what the magnitude of RPDQ is. Remember, RPDQ points from the DQ to the point P. So RPDQ is really this vector right here. This is RP DQ. So can anybody look at that and tell me what the magnitude of that vector is? So look at that diagram. Would y'all agree if I told you the magnitude is the square root of r squared plus y squared. You see, that's just a right triangle, right? And the vertical leg has a length y and the horizontal leg has a length r. Now all I have to do is say, what is RP dq, which remember, this is defined to be RP minus R dq. So I've already got RP. So I'm going to say R I hat minus Y J hat is RP minus R dq. So now I've already answered the three major questions. The three major questions were: one, dq equals question mark; two, RP equals question mark; and three, RDQ equals question mark. And once you have that, then all you need is number four. What is RP dq and the magnitude of RP dq. So that's what has to be done to use this formula. I now have it. I can say DE is equal to, I'm going to pull the, oh, actually, I'll just write the fraction bar really big. And the DQ is going to be lambda times DY. I have a 4, a pi, epsilon naught in the bottom. And then I'm going to take R squared plus Y squared. I've got to take the square root of that, but then I got to cube it. So I'm going to make it to the 3/2 power. Whoa. I made it to the 3/3 power by mistake. So there's the 3/2 power. And now I need the actual vector because the left-hand side is a vector. Well, that vector is R I hat minus Y J hat. Okay. So once you've gotten this part right here, you've actually done all the physics, or most of the physics. There's a little bit of physics left. You can use physics to figure it out, which I would argue that most people are not in a good spot at this point in their physics career, because at this point you're just learning this branch of physics, and therefore you might not realize certain things. So you'd have to defer to your mathematics by looking at the integral and seeing things like whether it's odd or even, that kind of stuff, and the ranges of integration. What I will tell you is that if you look at that DQ as I have it drawn right here, everybody see the DQ is up a distance y from the origin. Well, that's going to create an electric field that points. Let's show you how that points. That points that way. Now, if you consider an equivalent DQ down here, that's going to point this way, and by symmetry they're going to have the same magnitude and be at the same angle above and below the x-axis. So I think you can tell from that that any y component you have should be 0. That's the physics that you hadn't quite done yet. All the rest of the physics is done by just writing out that integrand that I had there. But by noticing the symmetry of the problem, that for each y, there's another dq at negative y, and by the symmetries of the Coulomb law, we see that each of those has the exact same but opposite in magnitude y component of the electric field. So we expect the y component of the electric field to be 0. So I'm going to say symmetry suggests that E sub y equals 0. Okay. Now you can also tell by looking at the integral is actually going to be y over the 3/2 power of r squared plus y squared. If I replace y with negative y, then I get negative y over r squared plus y squared to the 3/2 power, which is the opposite of what the original integrand was. And that means that the integrand is an odd function, and an odd function integrated over a symmetric range gives you an integral of 0. So that's the actual mathematical reason that the y component is going to be 0. Everybody follow that? Anybody have any questions about that? So I'll say also So hopefully you can read all that. So I'm saying also y over the 3/2 power of r squared plus y squared is odd, because if you replace y with negative y, you end up getting the negative of the original. So that means it's odd, and the range of integration is from negative infinity to positive infinity. That's a symmetric range of integration. And just like the sine is an odd function, if you integrate sine from, say, negative 1.07 pi to 1.07 pi, you will get 0. Same thing here, you will get 0. So we know that y component is going to disappear. So now we're in a place where we can actually compute the integral. So I have E, the electric field, is equal to the integral of dE, which I'm going to write this lambda out in front and this 4 pi epsilon naught out in front. And I'm going to say the integral of, now I have a dy times r I hat. Actually, was it r or negative r? Yeah, it was r. Yeah, because that's rp. Okay, r I hat over r squared plus y squared to the 3/2 power. Okay. And I'll say plus 0. But in reality, actually, let me not do that. I'll write it here and we'll make the change in a second. But I'm going to say, put this in square brackets. So lambda over 4 pi epsilon naught is in both of these. I'm going to say integral minus the integral of dy y j hat over r squared plus y squared to the 3/2. Okay. And then close that bracket. And this is the integral that I said was going to be 0 by symmetry. And by odd / even considerations. Okay. So that one's going to go to 0. You can actually carry out the integral. The integral quite easy. In fact, you can just do a substitution, let r squared plus y squared equal u, then du is equal to 2y dy. And you already have the y up top. And then when you integrate it, you'll see it's 0. But assuming we're not going to do that, I'm going to go ahead and say now I've got lambda over 4 pi epsilon naught. And I'm going to say let y equal r tangent theta. This is called a trig substitution. And that implies that dy is equal to r secant squared theta d theta. I should actually give myself a little more room than that. So I'm going to erase that junk. I'm going to erase this. I'm going to try to erase this. Okay. So now this implies that dy is equal to r secant squared theta d theta. And I can do some other stuff that I'm going to do a little bit later. So I'll just leave that space right there. I'm going to say now I've got lambda over 4 pi epsilon naught integral of r secant squared theta d theta over, now I've got r squared, which appears in both of them. So it'll be 1 plus tangent squared theta. All of this raised to the 3/2 power. And of course, all of it has an I hat after it. Okay. Now, I'll leave the space right here for something I'm going to do with that. But right now I can go ahead and see that 1 plus tangent squared. Does anybody recall what that trig identity is? One plus tangent squared is in fact secant squared. So when I take secant squared and raise it to the 3/2 power, I get secant cubed. Similarly, when I take r squared and raise it to the 3/2 power, I get r cubed in the bottom. So I'm going to have that. And I still have the r up top. And by the way, I already had an r, so this should have been r squared here. So let me put that there. And now I've got the integral of secant squared theta d theta over secant cubed theta. Okay, so obviously this is just 1 over secant theta, which is the same thing as cosine theta. And not only that, this just becomes r in the bottom. So I'm going to have an I hat here, but this is going to reduce to lambda over 4 pi epsilon naught r I hat times the integral of cosine theta d theta. Now, I could go ahead and plug the original function back in, but I don't necessarily want to do that because I can make use of this y equals r tangent theta like this. I can say y equals r tangent theta means that this is theta. Oh, that was bad drawing. Hold on. That this is y and this is r, and this is of course the square root of r squared plus y squared. So when I integrated from negative infinity to infinity, I was basically integrating from theta equals negative pi over 2 to theta equals pi over 2. Okay. Cosine is in fact an odd function. Or excuse me, is in fact an even function. And an even function integrated over a symmetric range is the same thing as integrating from 0 to the end and multiplying by 2. So I'm going to do that just to save a little bit of trouble. So I'm going to say 2 lambda over 4 pi epsilon naught r I hat is equal to the integral from 0 to pi over 2 of cosine theta d theta. And of course, the derivative of sine is cosine, so the integral of cosine is sine. So I now have lambda over 2 pi epsilon naught r is equal to the sine of pi over 2 minus the sine of 0, and all that times I hat. So the sine of pi over 2 is in fact 1, and the sine of 0 is 0. So this part right here is 1, and this part right here is 0. So my final answer is the electric field is equal to lambda over 2 pi epsilon naught r in the I hat direction. And remember that I hat direction is just a happenstance of the fact that I chose to put the point on the x-axis. By cylindrical symmetry, basically, if you take any point a distance r away from anywhere on the wire, you're going to have a strength of the electric field equal to the charge per unit length divided by 2 pi epsilon naught times the distance away, and it's going to point away from the wire perpendicularly. So in this case, it's just the I hat because that's the direction we chose the x-axis pointing, but in general, that's it. Now, we don't necessarily know lambda, but in this case, that was what I was giving you, is that the charge per unit length was lambda, and we got that answer. Okay. Now, that's one of the most difficult problems that you'll see the entire year. Okay, this entire course, including last semester's 241, that's probably the most difficult problem you'd see. That being said, it's completely doable. What I would consider doing if I was you was trying to do the extra credit that I listed, which is how close is too close, or how far is too far. I think that's what I named it, was how far is too far. But I'd also consider what if the wire went from, let's say, L to negative L over 2 or something like that. So it wasn't symmetric and it didn't go infinitely far. Or what if the wire went from L over 2 to negative L over 2? That's another way I could change this problem around. So I would try all three of those. I'd try one to close your book and notes and see if you can do this the same problem I just did. Once you get that nailed down, then try to do it for, instead of going from infinity or negative infinity to positive infinity, try to go from negative L over 2 to positive L over 2. And then once you get that, try to go from negative L over 2 to positive L, so it's not symmetric anymore. And in fact, you'll end up getting a Y component that's not 0. So all of those are different ways you can add it. Now, with that in mind, just so you can get started on the other stuff, we're obviously going to spend another day on this. I've got probably 3 more integrals that I need to show you. But you also need to know what that very first problem was. And that very first problem that I worked had a charge of Q and the opposite charge, in other words, negative of the other charge, a distance apart. See right here, they're a distance of 4 meters apart. Well, 2 charges opposite in sign, separated by a distance, is called an electric dipole. So there exists an electric dipole. And the electric dipole is generally thought to be a charge of plus and a charge of minus that are equal in magnitude. So this one has a charge of plus Q, and this one has a charge of minus Q. And in fact, they're a distance, let's say D, apart. Then the electric dipole, P, is defined to be Q times D, but it points, let's say there's a vector D that points from the negative to the positive, and that's the way you define it. So in other words, this particular dipole is represented by this vector right here, P. And that vector P is Q times D, pointing from the negative charge to the positive charge. That's what the electric dipole is. And in fact, when we go to work on things like the hydrogen atom or more specifically, or a better case would be the water molecule. The water molecule, it acts like a Mickey Mouse head, so that the oxygen is the head of Mickey Mouse, and it holds on to the electrons a little more strongly than do the two hydrogens. So the two Mickey Mouse ears, right in between them, there's sort of a net positive charge right in between those two ears, whereas down by Mickey's chin is a net negative charge. So the electric dipole would actually point from his chin up to halfway between his two ears. That would be the electric dipole, and you can just treat it like this. It's Q times D. Okay. When you do that, it turns out the electric dipole experiences a torque given by P cross E. And not only that, in addition to it having a torque, and your book does this derivation, okay, it's pretty straightforward. But in addition to that, it also has a potential energy associated with it, such that the potential energy is negative P dot E. So those are some very simple formulas that your book and your author and your teacher expects you to know how to use. You'll see them in the homework, but we've essentially covered all the hard stuff from chapter 21, except I need to do some more integrals. So next time, for starters, you should probably go and look at the other integrals that I've already provided you, and you should look at the integrals in your textbook, because the instructor or the author does them a little differently than I do. I do it in such a way that I think it's mathematically straightforward, but physically easy. Whereas he does it in a way that I think is physically complex, but mathematically pretty straightforward. So I'm of the belief that you guys understand math a little better than you do physics right now. So I'm trying to show you all the nuts and bolts and ins and outs so you can make some sense of it. That generally works for me. I have a high success rate in this class, so hopefully that'll be the case here. But either way, we're going to work several more, and we'll have the rest of the semester to work a lot of these types of integrals. You guys are actually done now. Definitely start checking out those videos of the other integrations I did. So I will do, for instance, instead of a long wire that's straight and has a charge per unit length, I'm going to take a wire and put it in the shape of a circle and have it have a uniformly distributed charge over it and a radius of big R. And I'm going to calculate the electric field directly over the center of that loop. Then I'm going to use that result to integrate it in an entirely different way to get the actual electric field above a disk of charge where the charge is uniformly distributed over the entire disk. Your book does those exact same problems, but it does them in a different way. I want you to have access to both ways. That's why I'm doing them. That's one of the reasons I'm doing them a different way. So that's it. You're free to go. Remember, when we come back on Monday, I will be finishing up some more integral problems that also might happen in, if I have any impromptu office hour type things. But also Monday we'll start into chapter 22. So you're free to go. I will wait till the last person leaves, and until then, I'll see you guys on Monday.
I have a quick question for this last integral you did.
Okay.
So how did you get from lambda over 4 pi to 2 lambda over 4 pi? Where did the 2 come into play?
Okay, so I went from integrating from negative pi over 2 to pi over 2. Cosine's an even function. That means cosine of negative theta is the cosine of theta. So instead of integrating from negative pi over 2 to pi over 2, I can multiply the integral by 2 and integrate from 0 to pi over 2.
Oh, okay.
That makes sense?
Yeah, and you can just put whatever bounds on the integral, and because we didn't have them at first, you just
Yeah,
feel for
I hinted to him, but I didn't really. I hinted to you that it was going to go to positive infinity and negative infinity. I just never wrote them on the actual integrals until that last part, and that's because I knew a change of variables
Gotcha.
was going to come. Anything else?
No, that was all.
Okay.
Thank you.
Notice, give that other integral a try, the j hat component, because that one, like I said, is really easy. You can just let u equal r squared plus y squared, and du is 2y dy. So you'd have to multiply by 2 and divide by 2, and that would give you 2y dy, which is just du on top, and you have a 1/2 out in front, but you'll integrate that and it'll come to 0. So that's another nice little practice integral for you.
All right. Have a good night.
You too, see you, Drew. Anybody else? Thank you, John. Thank you, Elron. You too, Elron. Antoine, do you have any
Professor.
questions? Yeah, Bohan, go for it.
Yeah, I just have a question about this. The P equals to QD. The direction. So for the D, the direction is a positive from positive to negative, and the P, the direction is from negative to positive, right?
Yeah, the P vector that we call the electric dipole,
Right.
that P vector has to point from the center of the negative charge to the center of the positive charge.
Yeah, so that is the direction that against the electrical field, right?
Yeah, it's exactly the opposite of the electric field that would be caused by it.
So
But
so in the formula, the D, the vector D, that direction is that from a positive to negative?
That's just a distance. That's the separation between the two. Like in the problem we worked at first, that would have been the 3 meters. So it has no direction associated with it. D is just how far apart they are. To make it a vector, you want it again to say, let's take that 3 meters and point it from the negative to the positive, and that'll make our D vector.
So that's not an actual vector.
Not until you make it one. Yeah, the D is just the distance between them. And then you say, well, I want it to be a vector, so I'm going to make it run from the negative charge to the positive. And then you just turn D into a vector.
Oh, okay. So it doesn't matter the direction, anything.
Right, exactly.
Okay. All right. Oh, also, Miss Younger, so the last question you were working on, is that kind of question we're gonna say on the exam or test? Like
Believe it or not, that integral is it's a very real possibility. Your book works it, and when it works it, it actually gives you or defines a formula for it.
mhm.
And if you'll notice, when they actually do that, I'm trying to look for it right now. When they actually do that, they give you the answer is lambda over 2 pi epsilon naught r, but they don't put a number by it. So what that means is every time they ask you to solve a problem
Mhm.
with that infinite line charge, they're sort of expecting you to rederive it. I think that's completely fair game to do that on a test. That's why I'm trying to stress you guys to do it those 3 different ways that I told you could vary it just to get some practice with it.
Okay. All right. Thank you.
Sorry, I wish I could give you better news, but I think it's a worthwhile skill. If you don't
Yeah.
get it, it's not the thing that's going to keep you from surviving as an engineer or physicist or whatever you want to be. It's just something that'll come later, probably.
All right. All right. Thank you.
You're
I
welcome.
give
See you,
you
Ron. Thank you. Anybody else have anything? I'm going to post this video as soon as it finishes rendering, and I'm going to post these notes right after I get offline. All right, I'm going to stop sharing. Anybody else have any questions before I log off? All right, looks like everybody's good then. Have a good evening, Gabrielle, and Josiah. Bye-bye.